Okay, good morning. So today we are going to start with another applications of partial differentiation. The first application for the partial differentiation was the Jacobian. Jacobian is a very strong tool for change of variables. So in this semester, we have learned this Jacobian, but its actual use is in the M2, where like for the integral in our 12th standard. So what we did was integral the integral x sine of x square dx. Okay, what you did was you simply put, I mean, x square, you can put x square is equal to t, so that will be 2x dx will become dt. So x dx is equal to dt by 2. And as there are no limits right now, it is indefinite integral, so no need to work with the limits. And what we have is sine of t dt 1 by 2 outside. So substitution is very much easy when you're dealing with one integral, but things become difficult when we have say double integral. The first integration is with respect to x, second is with respect to y, and function is of xy dy dx. Okay, so just try to understand the abstract behind this. Okay, when I'm doing double integral, the change of variable will be difficult there. Okay, so in that case, you will have to put some value for x, you will have to put some value for y. And in those types of cases, Jacobian will play a major role. Okay. So that's why Jacobian is one of the applications of the partial differentiation. Moreover, functional dependence is something that is very much important uh, when we are studying differential equations and the different theories. So that was the first application, and the next application about the partial differentiation that we are going to see today, which is the errors and approximation. So errors. So I'll talk about both the possibilities. I mean, let z is the function of f of xy. Okay. Say if you are finding out area, and it depends on two parameters x and y. And while finding out the area, you made some mistake in x while calculating x. You made some mistake while calculating y. So what will be the corresponding error in the value of z? That's what error does. So let z is equal to f of xy is a function of two variables, be the function of two variables, be the function of two variables. Okay. A delta x delta y, or dx dy in our terms, dx dy with the errors while while calculating x and y. So while calculating x and y, dx and dy are the errors. So correspondingly, dz will be the error in z. The error in z. So if you have made errors in x and y, so there will be some error in the value of z. So that is dz. Then b dx upon x, dy upon y, and dz upon z will represent what will be x and y here. X comma y will be the actual value of will be the actual value, sorry, calculated value be the value. So dx upon x will represent relative errors, represent a relative error in x, y, z respectively. Okay. So once these are the relative errors, so 100 into dx upon x will represent 100 into dy upon y, 100 into dz upon z will represent. Yes, anyone?
Percentages.
Percentage.
Percent percentage errors in x, y, z respectively. Look, the same thing can be done for u is equal to f of x, y, z. If I have u is equal to f of x, y, z, then dx, dy, dz are the errors while calculating x, y, z. So correspondingly, du will be the error in the value in u. Then 100 into dx upon x, 100 into dy upon y, 100 into dz upon z will represent percentage errors in x, y, z. So correspondingly, percentage error in u will be given by 100 into du upon u. So that is all the theory part about the error function. So once we understand this dx, dy, dz, and then 100 into dx upon x, dy upon y, and dz upon z. These are the percentages. These things we are going to need. Now, how do we proceed here? Okay, so let's start with the function z is equal to f of x comma y. Okay, now there is some error. So there is a small change in the value of delta x, be the small change in the value of x and y. So the new value that we will get of x plus delta x, comma y plus delta y. And if I subtract f of x comma y from this, what I should get? What I should get?
DZ or delta Z, sorry.
Delta z. So when I say f of x plus delta x, y plus delta y, what I am going to get is z plus delta z and minus this z. So that is ultimately delta z. So now what I about z. So if there is some error, so I need this error in. So delta z is equal to Now, let me just remind you what we have seen is we have seen this x plus h Taylor series. So f of x plus h in the Taylor series was given by f of x plus h into f plus h square by 2 factorial f double dash of x and so on, right? So here I was working with one variable. The Taylor is for two variables also, where we have f of x plus h, y plus h, and this can be expanded, okay, in a Taylor series. We won't go into the details, but just uh, remember this, okay, how I'm going to get this. So I will expand this f of x plus delta and y plus delta y using Taylor series, in which the first term is f of x comma y, and the second term is delta f by delta x dx plus delta f by delta y dy. So on. Okay. So these are the first two terms. Higher powers we will neglect. Okay. We will assume that the error part is very much small in the higher power terms, and that's why what we do is we just consider the first two terms. So f of xy and f of xy will get cancelled out in this, and what we get is delta z is equal to, or delta z is equal to f by delta x delta x delta by f by delta y delta y. This is what we get. Now I'll take limit x comma y tends to 0, and what we get is dz is equal to delta f by delta x dx plus delta f by delta y dy. So this relation is going to represent the error inside. So you can note this relation down. This theory part is never asked, but this I explained just for the understanding. And what you have to remember, this represents error in with respect to errors in x, and what are the errors in x and y? Dx is the error, dy is the error. Y can find out. When we put the values, we will get actual error inside. Again,
सर सर आपकी स्क्रीन फ्रीज हो गई
yes,
है। वो जो लिखा है वो मतलब जिधर आपने लिखा है एफ ऑफ एक्स प्लस डेल्टा एक्स कॉमा वाई प्लस डेल्टा वाई माइनस एफ ऑफ एक्स वाई, उसके बाद कुछ भी नहीं लिखा हुआ दिख रहा है।
यस सर, सबको वही प्रॉब्लम है।
अच्छा। visible properly? Hello, am I audible? Anirudh?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So what I was explaining is, if you expand this Taylor series for two variables, if we use this, in which we will have the first term as this, and f of xy, and the second term is this. So we just take these first two terms, considering that higher power terms has less data. I mean, that is negligible. And when we take it, so we get this relation, the squared one, dz is equal to this. So this is what you will have to remember. So if we have function of two variables, error in z corresponding to the errors in x and y will be given by this relation. And as I said, nothing particular about two variables can be done for three variables also. So du is equal to partial derivative of f with respect to x dx, partial derivative of f with respect to y dy, partial derivative of f with respect to z dz. This will represent the error in u with respect to errors in xyz when you have function u as the function of xyz. Okay, so that is all the theory part about error functions. While solving examples, it is very easy. I mean, uh, anyone can do it. There is nothing difficult in it. So let's start with some of the examples here. Example. Find the percentage error. Find the percentage error in the area of ellipse. In the area of ellipse when
YAB.
an error of 1% is made in measuring its major and minor axis. Its major and minor axis. Okay, so first of all, ellipse, the equation is, I'll just write it down here since it is not necessary in the solution. So ellipse x square upon a square plus y square upon b square equal to 1. And the area of ellipse is pi AB. Okay, so let A comma B be major and minor axis. So what is given to us? Percent error in major axis and minor axis. How is the percent error represented? Hundred into
By
and dA by A. This is the percent error in A. The value is 1. Also, the percent error in B is equal to 1. To find, we have to find the percent error in the area of ellipse. So area, say capital A, 100 into dA upon A is something that we have to find out. We know that A is equal to pi A B. There are two ways to do this. One is by using the formula. Okay, I'll do it both the ways. I'll take log first of all. Log A is equal to taking log. So log A is equal to log pi plus log A plus log B. Now differentiating. Now differentiating, we have, so differentiating this log A will have 1 upon A dA is equal to derivative of log pi being constant 0 plus derivative of log A small a 1 upon A dA plus log B का derivative 1 upon B dB. Differentiating
1/100.
multiplying by 100 multiplying by 100. So what we get here is 100 into dA upon A is equal to 100 into d of small a upon A plus 100 into dB upon small b. Let's put the values here. 1 plus 1, the answer is 2. So if you have made 1% error while calculating major and minor axis, the percent error while calculating the area that you will get is 2%. Okay. So whenever there is a product, it is better to take log, because it directly after differentiating you will get almost the required expression. 100 into dA upon A. We need to put this value. The other way is, I will write out the other way over here. A small square, just to explain, because in some example this way is needed. Log won't work in that. So I have pi b, right? So dA will be given by partial derivative of A with respect to small a into dA plus partial derivative of A with respect to B dB. Put the values. So partial derivative of A with respect to small a, that is going to be pi b into dA plus partial derivative of A with respect to B, that is pi a into dB. This is the value of dA. I want to get this equation, dA upon A dB upon B. So what I'm going to do, I'll divide whole equation by A, capital A. Capital A. What is capital A? Capital A is nothing but, again here I am writing down. So dA upon A is equal to pi B upon pi AB dA plus pi A upon pi AB dB. Pi B will get cancelled out. So we have got dA upon A, dB upon B. So both the ways you can do it. Am I clear? I mean, I hope I have made myself clear. There are two ways to solve error examples. One, you take log and you take the derivative. The other way is use the expression that I made, while that is dA is equal to partial derivative of A with respect to the first variable dA plus partial derivative of A with respect to second variable dB, and just go on putting the values. Okay, fine. Next example. the area of a triangle, the area of a triangle is calculated using 1 by 2 B C sine A, which is equal to delta. Then the errors of 1%, 2%, and 3% respectively are made in B, C, and capital A. Full stop. If the correct values are correct values of correct value, actually not this. Correct value of A is 45 degrees. Find the percent error. Find the percent error in calculated value of delta. Can someone try this? So what we have, delta is equal, what is given first of all? 100 into dB upon B is equal to 1. 100 into dC upon C is equal to 2. 100 into dA upon A is equal to 3. What are we supposed to find here is 100 into d delta upon delta. What we have, delta is equal to B C sine A 1 by 2. Once we take log, we'll have log delta is equal to log half plus log B plus log C plus log of sine of A. Differentiating, we will have d delta upon delta is equal to 0 plus dB upon B plus 1 upon C dC plus 1 upon sine A into cos A. That will be cot of A dA. Multiplying by 100, putting up the values. When we multiply by 100, we have 100 into d delta upon delta is equal to 100 into dB upon B plus 100 into dC upon C plus 100 cot A as it is, cot of A in bracket 100 into dA. Now from this expression, 100 into dA upon A is actually 100 into dA is equal to 3A. So we can put this value there, and what we get is 100 into d delta upon delta is equal to 1 plus 2 plus 3A cot of A, which is nothing but 3 plus 3A cot of A. This is 100 into d delta upon delta. They have said that the correct value of A is 45 degrees. So let's put that in the equation. 45A is pi by 4. 3 plus 3 pi by 4 into cot pi by 4, which is 1. So the percent error while calculating delta is 3 plus 3 pi by 4. Clear? Fine. Next example. This will example. Find the possible percent error, possible percent error in computing parallel resistance. In computing parallel resistance. R of the resistance R1, R2, R3 from the formula 1 upon R is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. If R1, R2 and R3 are each in error by plus 1.2%. Yes, what we are given 100 into dr1 upon r1 is equal to 1.2. 100 into dr2 upon r2 is equal to 1.2, and 100 into dr3 upon r3 is equal to 1.2. So to find 100 into dr upon r, so let's start with the formula. 1 upon r is equal to 1 upon r1 plus 1 upon r2 plus 1 upon r3. Look, log won't work. If you take log, what you will get on the right hand side is log of 1 upon r1 plus 1 upon r2 plus 1 upon r3. So this cannot be written as log of 1 upon r1 plus log of 1 upon r2 plus log of 1 upon r3. Okay, this is not true. So I cannot take log here. So log will be useful only when you have product in the formulas. Okay, whatever formula you are using, if there is a product, then you can take log and calculations will be easier. Otherwise, we will have to go by the other technique. What is the other technique? You take the derivative and dr. So derivative of 1 upon r is minus 1 upon r square dr. Derivative of this with respect to r1, it will be 1 upon r1 square dr1 plus, no sorry, minus 1 upon r2 square dr2 minus 1 upon r3 square dr3. So I'll multiply by 100 here, minus 1 upon r I will keep outside, and I will have 100 into dr upon r. The same thing I will do in each and every term, minus 1 upon r1, and in the other bracket 100 into dr1 upon r1 plus in bracket minus 1 upon r2, 100 into dr2 upon r2 plus minus 1 by r3 in the other bracket 100 into dr3 upon r3. Now we have all the values. We can put that in the equation. So that will be minus 1 upon r to 100 into dr upon r is equal to minus 1 upon r1 in bracket 1.2 plus minus 1 upon r2 into 1.2 minus 1 upon r3 into 1.2. So 1.2 can be taken out with minus sign. So minus 1.2 and in bracket 1 upon r1 plus 1 upon r2 plus 1 upon r3. The left hand side is minus sign outside 1 upon r 100 into dr upon r. So this minus sign will get cancelled out. 1 upon r will get cancelled out with this term. So what is the answer? The percent error in this term is 100 into dr upon r is equal to 1.2. Any doubt?
No, sir. No, sir.
Fine. The same thing can be done to find the approximate values. Okay, only if some of the students are lucky enough to give theory exam, then they may have to do this type of example, and which is find 3.82 square plus 2 into 2.1 cube bracket complete raised to 1 by 5 by theory of approximation. By theory of approximation. theory of approximation also works on the same formula that we studied. So dz is equal to partial derivative of f with respect to x dx, partial derivative of f with respect to y dy. The same thing is going to work here. So we will have to first of all fix up the actual value. So actual value is so whatever calculated value is, so x is equal to 4 and the error in it is 4 minus 3.82. Okay, so 3.82 minus 4, sorry. So dx is going to be minus 0.18. The value of y I will fix as 2. So dy is going to be dy is going to be, okay, let me just explain this first of all. See, there are three terms we are working with: calculated x, error delta x, and the actual value of x. Actual value. Okay. So calculated x and the error, that is going to give me x plus delta x that is the actual value. Okay. So in this case, value of x with error, what I am assuming, that is 4. So the actual value of x is going to be x plus delta x, right? So if I want to find this 3.82, which is the actual value, so 3.82 has to be this. So delta x is going to be 3.82 minus x. I hope I have made myself clear now. So this is something that you have to understand. Now, so similarly, dy is going to be, what is our actual value? 2.1 minus the value of y that I am assuming 2. So dy is going to 0.1, right? What I want to find is complete term, which means that to find, what you are going to find out, the value of this expression, that will be, say, what is our function here? Z is equal to x plus 2 times y cube total raised to 1 by 5. So what you are finding out here, z plus tz. Is anyone having doubt over here now? Pratik, are you clear?
Yes, sir.
Now, so we need to find z as well as dz. First of all, z is equal to, put the value of x there. X is 4 square plus 2 into 2 cube total raised to 1 by 5. So this is 16 plus 16. 2 cube 8, 8 into 2, 16 raised to 1 by 5. So 32 raised to 1 by 5 is 2. Okay. Now we need to find dz. Dz is equal to, what is the formula? Partial derivative of f with respect to x dx plus partial derivative of f with respect to y on dy. What is the derivative of this term? X square plus 2y cube raised to 1 by 5 with respect to x. I'll write it down in bracket. 1 by 5 x square plus 2y cube raised to 1 by 5 minus 1. By chain rule, derivative of x cube plus 2y cube with respect to x, which will be 2x, bracket complete dx, plus the other bracket 1 by 5 x square plus 2y cube raised to 1 by 5 minus 1 into derivative with respect to y. So that will be 6y square dy. Now you can put our values in this. So this is equal to, I'll take common, 1 by 5 minus 1. So that will be x square plus 2y cube raised to minus 4 by 5. So I'll write down 1 upon 5 into x square plus 2y cube raised to 4 by 5 in bracket 2x dx plus 6y square dy. So we can put the values of x and y, dx, dy in this. So 1 upon 5 into x square, 4 square 16 plus 16, 32 raised to 4 by 5 in the bracket 8 into minus 0.18 plus 6, 4, 24 dy is 0.1. So finally, we solve this, dz is going to be 0.012. So z plus dz is equal to 2 plus 0.012. The answer is 2.012. Anyone having doubt in this?
No, sir.
Anirudh,
No doubt. No doubt.
no doubt. Daksh, where is Prabal?
Yes, sir.
Is it clear or you have any doubt in this?
No, sir, it's clear. It's clear.
Okay, fine. Can try one example now.
Sir, can you show this screen, previous one? Okay, sir, done.
Example. A power dissipated in a resistor is given by P is equal to E square upon R. Find percent error in P. When E is increased by 3% and R is decreased by 2%. What will this increased and decreased mean?
So the positive and negative error.
So when there is decreased, 100 into dr upon r will become -2. Okay. And increased 100 into dE upon E will be equal to +3, whereas 100 into dr upon r will become -2. Find the percent error.
So the answer is 8%.
Yes, sir, 8%.
8. What is the answer?
So 8.
8%.
Wrong. What do you have to 100 into dr upon r? The 100 into dr upon r is -2. What you are taking is +2.
Oh no,
Look,
sir, but
No,
R
sir.
is, R is in
8 answer.
denominator, so it will be
दो बार
minus there as well.
जाएगा
100 into dp upon p is equal to 2 into 100 into de upon e. Am I right?
yes
Yes, sir.
Minus.
minus of minus
Why minus of minus? Yes,
Sir,
sorry.
yeah.
Yes. Okay, fine. Answer is 8. Okay, that's all about errors and approximations. In the next lecture, we'll study maxima and minima for two variables. Maxima and minima you have already done in your 12th standard, but that was for the function of one variable. Okay, and now we are going to see for the functions of two variables. Fine. We will stop here. Please put your name and roll number in the chat box.